Hi friends, in this video we are going to draw phasor diagram of single phase transformer for resistive load. Before drawing a phasor diagram, let's see equivalent circuit diagram of a single phase transformer when it is loaded. So it is like this. So basically we are going to make use of equivalent circuit diagram in order to draw phasor diagram. So if this is a equivalent circuit diagram of a single phase transformer on load with different values of voltage, current, resistance, reactance listed, let's start with a phasor diagram with a resistive load. Whenever we have drawn an equivalent circuit diagram and listed out all voltage and currents, finally we got V2 terminal voltage. We started with V1, but in case of a phasor diagram we will follow reverse order. That means first we will draw phasor V2 and we will progress like this and get the V1. So the first phasor is V2. Now second phasor, I am going to draw second phasor of I2. Why? Because I know the phase relationship of I2 V2 for resistive load. I2 V2 are in phase for resistive load. So it will be like this. I2. Now this I2 flows through R2 as well as X2. R2 pure resistance, so it will give rise to a voltage drop I2 R2 which will be in phase with I2. So I can draw third phasor like this, I2 R2, which is nothing but voltage drop across R2. Obviously it will be in phase with I2, but I have drawn from the tip of V2. Next, current I2 flowing through the pure inductor X2, hence it will give rise to a voltage drop I2 X2, but that will be leading I2 by 90 degree. So for pure inductor, I2 X2 will be like this. Now, if I apply KVL to secondary side circuit, so V2 plus I2 R2 plus I2 X2 will be E2. So KVL at secondary side will give me V2 plus I2 R2 plus I2 X2 is nothing but E2. So I will get a vector E2. Secondary side phasor diagram is over. Now E2 is the EMF induced because of flux phi. So we have seen while writing EMF equation, flux phi is responsible for induction of E1 and E2 both, and flux phi leads EMF by 90 degree, or you can say E2 E1 lags flux phi by 90 degree. If I know E2, obviously flux phi will be 90 degree ahead for this E2. So flux phi will be like this. Same flux phi is responsible for production of E1, EMF induced at primary side. If I consider number of turns at the primary less than number of turns on secondary, obviously E1 will have less value compared to E2. So I will represent E1 like this. Now, flux phi is produced because of this circuit, and the current responsible for production of flux phi is I mu. So since flux phi is known to us, obviously the current who is responsible for production of this is also known, and that will be in phase with this flux phi. So this will be the current which I can say I mu for responsible of flux phi, that will be in phase with phi. Now, because of Lenz's law, the EMF that will come across this is minus E1. So I need to know what is minus E1. So minus E1 will be equal and opposite to that of E1. So minus E1 will be like this, equal and opposite to E1. So minus E1 is nothing but voltage across this, which I can say a voltage across resistance RC, and current flowing through the RC is IC. So obviously this IC and this minus E1 will be in phase. So where will be IC phasor? It will be in phase with the minus E1. So this is IC. If I apply KCL at this node, I can say IC and I mu. If I add, I will get I0. Obviously it has to be a phasor addition. So phasor addition of IC and I mu will be I0, which is no load primary current. So if I add IC and I mu, I will get I0, which is nothing but no load primary current. Now, once again I can apply KCL at this node. I0 and I2 dash is nothing but I1. So I need to know I2 dash. I2 dash is nothing but that current which will nullify the effect of phi 2, which is caused by I2. So obviously it should be opposite to that of I2, but the magnitude depends upon the turns ratio. So I2 dash I will consider opposite to I2, and the magnitude it depends upon ratio N1 and N2. So I2 dash will be like this, opposite to I2, and phasor addition of I0 and I2 dash will be nothing but I1. So phasor addition of these two will be nothing but I1. Now this I1 is going to flow through this R1 and X1 and give rise to two voltage drops, one across resistance and another across reactance. So for resistance, voltage in phase with the current. So if I know this current, obviously the voltage is in phase with this, you can say parallel to this. So it will be like this, parallel to I1, and from tip of minus E1 I will draw. So this is I1 R1. Now drop across pure inductor. So voltage across pure inductor leads current by 90 degree. So if this is a current, obviously voltage drop will be 90 degree to this. So I will draw phasor like this, I1 X1 leading I1 by 90 degree. Now if I apply KVL to primary side circuit, minus E1 plus I1 R1 plus I1 X1 will be nothing but V1, minus E1 I1 R1 plus I1 X1 will give you V1. So V1 will be like this. A primary side voltage. We started with V2 and end up on V1. Here two phase angles you will get. One is this, which we call as Phasor, no load power factor angle, and second is this, which is nothing but Phi1, angle between V1 and I1. So whenever we draw a phasor diagram, we need to understand and remember certain equations. So the very first equation that we got is at the secondary side. And what was that? It was this: V2 bar plus I2 R2 bar plus I2 X2 bar is nothing but E2 bar, because you are applying KVL to the secondary side circuit. Similarly, at the primary side, we need to remember two KCL equations. One for this, IC and I mu is nothing but I0. So IC bar plus I mu bar is I0 bar. No load primary current. And another KCL equation you have to remember is this: I0 and I2 dash will give you I1. So I0 bar plus I2 dash bar is nothing but I1 bar. And third KVL equation is at the primary side. And what is that? Minus E1 plus I1 R1 plus I1 X1 is nothing but V1. So minus E1 bar plus I1 R1 bar plus I1 X1 bar is nothing but V1 bar. So by knowing the equivalent circuit diagram perfectly and some basics of phasor diagram, you can draw phasor diagram of a transformer at any load. Now we have seen phasor diagram of a single phase transformer for resistive load. Let's do it for inductive load. Or you can say lagging power factor load. Let me tell you one thing. If you have understood a phasor diagram for resistive load, getting a phasor diagram for inductive and capacitive is very easy. Why? Because it is absolutely similar to that of a resistive load. Only difference is that location of I2 with respect to V2. So let's draw it. So obviously I will start with a V2 phasor. It's a lagging power factor load or inductive load. In the inductive load, current lags voltage by angle phi. So if I know V2, I can draw phasor of I2 lagging behind V2 by angle phi 2. It's a power factor angle of a load. Now I2 is flowing through two elements, R2 and X2, give rise to two voltage drops. I2R2 and I2X2. I2R2 will be in phase or parallel to the I2, so it will be like this. And I2X2 being a drop across pure inductor, it will be 90 degree to this. If I apply KVL to the secondary side, what I will get? V2 bar plus I2R2 bar plus I2X2 bar is nothing but E2 bar. So if I add these three phasors, I will get secondary side induced EMF E2. Who is responsible for this? Is nothing but flux phi, which will lead this E2 by 90 degree. So flux phi will be like this, 90 degree ahead of E2. Same flux phi is responsible for production of E1, primary side induced EMF. Now, by Lenz's law, I need to know minus E1. So minus E1 will be equal and opposite to E1. Minus E1 is a voltage across this part of the circuit. Pure inductor and pure resistor. For pure inductor, the current lags voltage by 90 degree and that current is I mu. So I mu lag minus E1 by 90 degree, which will come in phase with this flux phi. So I mu will be like this. And IC is a current flowing through the pure resistance RC. It will come in phase with minus E1. And if I apply KCL here, what I will get? I will get no load primary current is nothing but phasor addition of IC and I mu. So if I add these two, I will get I0. No load primary current. Now there will be an effect of this I2 that need to be nullified, that is nullified by I2 dash current. So I need to know what is I2 dash. So I2 dash is nothing but equal and opposite to I2. I cannot say equal rather, but it is definitely opposite to I2. So I will draw I2 like this, which is nothing but I2 dash. And once again, if I apply KCL over here, I0 and I2 dash is I1. So I1 bar is nothing but I0 bar plus I2 dash bar. Phasor addition I need to do. So if I add these two phasors, I will get I1. This I1 is going to flow through R1 and X1, give rise to I1 R1, I1 X1 voltage drops with some phase angles with respect to I1. Being a pure resistance, I1 R1 will be in phase or parallel to this I1, so it will be like this. And I1 X1 is a voltage drop across pure inductor which will lead this I1 by 90 degree. So it will be like this. And phasor addition of these three will be nothing but V1. So minus E1 bar plus I1 R1 bar plus I1 X1 bar equal to V1 bar. So if I add these three phasors, I will get V1. I started with V2 and I got V1 as the last phasor. Angle between V1 and I0 is no load power factor angle, which is phi 0, and angle between I1 and V1 is phase angle phi 1. So this is what a phasor diagram of a single phase transformer when inductive load is applied. Let's go for capacitive load. Capacitive load can also be called as leading power factor load. Getting a phasor diagram for capacitive load or leading power factor load is absolutely similar to that of phasor diagram for lagging power factor load. Only difference is location of I2 with respect to V2. So let's see. I will start with a V2. Being a leading power factor load, current I2 leads V2 by angle phi 2. So I2 will be like this. And the angle between V2 I2 is phi 2. I2 is flowing through secondary resistance R2, giving rise to a drop I2 R2, which will be in phase with I2. Same current is flowing through pure inductor, giving drop I2 X2, which will be 90 degree ahead that of I2. So it will be like this. And KVL to secondary side will give rise to V2 bar plus I2 R2 bar plus I2 X2 bar is nothing but E2 secondary side induced EMF. So phasor addition of V2, I2 R2, I2 X2 will give rise to E2. E2 is the EMF induced at the secondary side because of flux phi. So that flux phi will be ahead of E2 by 90 degree. So this will be the location of flux phi. Same flux phi is responsible for production of E1. At the primary side, I know because of Lenz's law, minus E1 will be the voltage that actually across this part of the circuit. So minus E1 is nothing but equivalent opposite to E1. So equivalent opposite to E1 is minus E1, which is nothing but a voltage across pure resistor and pure inductor or parallel combination of RC and XM. So for resistance, the current IC will be in phase with minus E1, and for XM the current will be lagging minus E1 by 90 degree. So ultimately it will come in phase with flux phi. Now phasor addition of IC and I mu will be no load primary current. So if I add these two currents, I will get no load primary current I0. I2 is the current flowing at the secondary side. Because of that, flux phi 2 will be there, which will reduce the main flux. In order to avoid this, primary current should have some extra component called as I2 dash. So I2 dash will be opposite to I2. And phasor addition of no load primary current and I2 dash will be primary current I1. So if I add these two, I will get primary current I1, which will flow through resistance R1 and X1, giving rise to I1 R1 and I1 X1 drops respectively. I1 R1 will be in phase with I1. So the voltage drop will be parallel to I1 like this. And I1 X1 will be 90 degree ahead of I1. So it will be like this. And phasor addition of minus E1 bar, I1 R1 bar and I1 X1 bar equal to V1 bar. So minus E1, I1 R1, I1 X1 will be nothing but V1. So V1 will be like this. So we have started our journey of phasor diagram from V2 and ended on V1. In this process we got two phase angles at no load, that is angle between I0 and V1, which we call as Phasor, and between V1 and I1, that we call as Phi1. So based on the equivalent circuit diagram of a transformer and certain laws, that is KVL and KCL, we can get phasor diagrams of a single phase transformer when resistance is applied as a load or inductive load or capacitive load. Thank you.